So, good morning once again. Am I audible, Sandeep sir?
Yeah, you are audible.
Okay.
Sir, you're
A warm welcome to Sandeep Chakravarti sir from IIT Kharagpur. So, I welcome all the participants once again on session number 2 of day 2. So, Sandeep sir will be talking about permission and permissionless blockchain. So, now I request Sandeep sir to please start the session. Thank you, sir.
Thank you. Thank you. So, thanks to Dr. Patnaik for inviting me in this FDP program. So, in today's session, I will broadly talk about the basic idea behind the consensus protocols in blockchain. So, I'll cover both the permission and permissionless blockchain. So, before going to technical topic, just a bit of introduction about myself. So, I'm an assistant professor at Computer Science Department at IIT Kharagpur. So I lead a team on computer systems who are looking into various aspects of computing and looking into the platforms and systems for supporting large-scale computing and large-scale application development. So being mostly a system guy, from the blockchain perspective, I focus on the system aspect of it rather than the security or the application aspect of it. So we are working long on this particular topic called consensus in case of blockchain, as well as different kind of cryptocurrency protocols or the cryptocurrency systems. So we are looking into that, how efficient or effectively you can design a consensus protocol for such kind of large-scale distributed system, which can also can be applied for the blockchain perspective. So with that, let me go to the technical part of today's talk. So I am assuming that by this time you already have a basic idea about blockchain, what blockchain is and how it looks like, what is the basic data structure that is being used in blockchain. Now, just to start or just to recap, as you already know that blockchain is nothing but a kind of decentralized data structure. By the mean of decentralization, it is also a kind of distributed data structure where there are the blocks which contains the transaction, and we use the cryptographic hash to connect individual blocks, ensuring a tamper-proof chain of blocks and ensuring that this entire data structure, although it is decentralized or distributed, it is immutable. That means no one will be able to change anything in that data structure without others noticing it. So that is the basic principle or basic idea behind blockchain. And the beauty of the blockchain is that it works in a perfect decentralized setup where there are participants who do not trust each other. Out of those participants, there can be participants who are malicious, and they are trying to make an attack over the system by changing the information or changing the perception about the data. But the way we ensure the underlying system is that if someone is making a change in one of the block, that gets noticed by the valid participants in the system, and that way we try to prevent such kind of attack on the system. So that means the correct participants in the system, they would always be able to identify that which are the correct blocks and which are the wrong blocks or invalid blocks, and they should be able to discard the invalid blocks and should be able to accept the correct blocks. So this is broadly the basic philosophy behind the blockchain architecture, and the entire beauty within the blockchain architecture is its decentralization. So in terms of a distributed system, it is kind of similar to a distributed replicated database, where every participant in the network has an entire replica of the blockchain, and you need to ensure that everyone or every participant has the same copy of the block with them, or the same copy of the blockchain with them. So that is the kind of broad idea that possibly you already have gained from other talks, and you know that what blockchain is and how it looks like. Now, in this talk, in this particular talk, I primarily focus on the consensus protocol in blockchain, which is the core system protocol in the entire architecture, and which ensures that the correctness of the system is being maintained, and at the same time, it prevents any kind of attack which can happen over such kind of decentralized system. So that is the basic philosophy of today's talk. Now, just before going to the technical session, point to for all of you that I always prefer to have a session which is interactive rather than myself talking all the times. If you have any question or anything, any comments, feel free to stop me. You can always post a question in the chat box, so I can periodically look into the chat box to see if there are any question, and I would be happy to answer them. So, with that perspective or that background in mind, let us start about today's talk. So, let me start with the notion of distributed consensus. So this entire idea of blockchain consensus actually came from a year-old topic. So this concept of distributed consensus was introduced by Lamport in early 1970s, and in the domain of distributed system, these consensus algorithms have been well studied. There are a number of different kind of consensus protocols like Raft, Paxos, practical Byzantine fault tolerant, or BFT group of protocols. All those things were already there in the literature of distributed system. But the interesting aspect which is there in a blockchain-based architecture is its openness. So we'll see from a while that why do we need to revisit these consensus protocols in the context of blockchain, and why we should start thinking about them. Although the topic is a kind of, as I have mentioned, it is age-old topic. From 1970s, people have started doing research on distributed consensus protocol, and there are very fundamental theory behind the design of the consensus protocols, and primarily the Byzantine fault-tolerant group of protocols, where already there is a huge set of literature. But still, in the context of blockchain, we need to revisit those protocols, and we need to look into them from a different perspective. So I would try to boost you with that particular perspective, so that you can think of that what can be the different possible variation, and in which way people are actually thinking of designing new set of protocols for such kind of systems. So that way I start from the notion of the distributed consensus. So the distributed consensus ensures that different nodes in the network see the same set data at nearly the same point of time. So that is basically a kind of formal definition about distributed consensus. So if you are thinking about entirely a complete distributed system where every individual node has a common view of the system, so you need to ensure that every node is having the same view about the system, because otherwise, if I have one view of the system and you have a different view of the system, and whenever we are going to run a distributed protocol on top of those views, then we might end up with different results, and that is not desirable. So in a distributed system, I need to ensure that when every node, every individual participant runs some algorithm, everyone should lead to the same result. And to ensure that, what you have to maintain is that the input to the algorithm is same for all the users. So now you can imagine it in this way, that the input to the algorithm is some form of data or some form of state of the system. Now, when the input is some form of data or some form of state from the system, if all the nodes, all the correct nodes rather, are not on the same state, or if they do not have the same view of the data, then whenever they are going to run some algorithmic state, each one of will result in different output. And obviously that is not desirable. We always want that everyone get the same output, and as a result, the entire distributed algorithm which is running, it produce a single and unique output, across all the correct participants in the system. So to ensure that, we need to provide same view of the system to all the participating nodes, or rather all the correct participating nodes. So this is the notion of consensus. So we say that all nodes in the network need to agree or consent on a regular basis that the data stored by them is the same. So you need to remember that in a distributed system, we do not have any kind of single point of failure. So the entire data is decentralized. That means everyone is maintaining their own copy of the data. I do not have a central server where the data is there, and that way it becomes easier for me to make a consensus about the data. But here that is not the case. Everyone has their own copy of the data. So the major challenge in such kind of consensus algorithm is that, see, if every node is correct, okay, so that is the most trivial scenario. But to start with, just assume that all the nodes are the correct nodes. Now, if all the nodes are correct nodes, then getting consensus is trivial, because you can simply have a voting mechanism, and based on the voting mechanism, you can decide that what should be your decision, because every node is correct and they are going to respond with their correct decision. So, for example, if I just try to find out that, say, assume that this is not a virtual talk, this is a physical talk, and so currently I see there are 93 participants among us. Now, if I assume that this is a physical talk, and after the talk we need to decide that we want to go for a lunch, and I have two different restaurants, restaurant A and restaurant B. Well, and I need to decide that whether I want to go to restaurant A or restaurant B. Now the question comes that how will you make a consensus among these 93 or 94 participants that we should go to restaurant A and not restaurant B, or we should go to restaurant B and not restaurant B. So a simple way of doing that is to take a vote, right? I can be act as a leader. I can tell you that, well, here are the two options, restaurant A and restaurant B. Now you individually tell your choice whether you want to go to restaurant A or whether you want to go to restaurant B. Now all of you are giving the vote, and after I am receiving the vote, I am finding out, say, what is the majority opinion. If the majority of the people says that, well, I want to go to restaurant A, then we will go to restaurant B. If majority people says that, well, we want to go to restaurant B, then I will go to restaurant B. So using a simple voting technique, I can reach to a consensus. But the problem will come when the system is not this much perfect. So there are different kind of failures in the system. There are different kind of failures in the system, in the sense the easiest type of failures are kind of crash fault or the network fault. It is something like that. Say some of you are giving your response, but because the network is unreliable or the channel is unreliable, I am not getting your response. Okay. So that is one type of fault. If I am not getting response from someone of you, then it would be difficult for me to decide whether the majority agrees on restaurant A or whether majority agrees on restaurant B. But this is a kind of simple type of failure. There can be more complicated failure. For example, some of the participants among these 94 participants can be malicious. Malicious in the sense, say they already have a setting with restaurant A, they want to promote restaurant A. So what they do, although restaurant B is better than restaurant A, they give a vote for restaurant A. Well, or they can collude others, they can convince others for their own benefit that, hey, we should go to restaurant A rather than restaurant B. Well, but although globally restaurant B is much better than restaurant A. Now, under the presence of such kind of malicious nodes or malicious participants, it is extremely difficult to reach to a consensus, or rather reach to a correct consensus. And that is the challenge of any kind of distributed consensus protocol, that you need to reach to a consensus in the presence of a failure. Okay. So as I have mentioned, that starting from early 90s, a large number of works have been devoted on the development of consensus algorithms over a network. And the basic philosophy is based on message passing, as I have given you the example, like inform your current state to others so that everyone can match their current state with others in the network. So it is something like that in case of a distributed protocol. Every node will periodically inform their current state with others, ensuring that all the nodes have a complete view of others and they can select the majority decision or the majority the view of the majority of the nodes and update their current state accordingly. And that way, you ensure that all the correct nodes are on the same page. However, if you are relying on a distributed consensus mechanism based on message passing, you require that the participants in the consensus algorithms know each other. And that is the basic limitation for any kind of message passing based system. So in any kind of message passing, if you want to send some message to other participants, first you need to ensure that you know all the participants or all other participants in the system. So that is the kind of primary assumption that you have. But the question here comes that can we achieve consensus even when the network is arbitrarily large and no participants in the network really knew all other participants? Now, if you think from the blockchain perspective, you see our permissionless blockchain actually follows this kind of model. So in case of a permissionless blockchain, any participant can join in the blockchain network any instance of time, and they do not need to know who are the other participants in the network. And this network can be arbitrarily large. Well, now under this scenario, the question comes that can we still design a consensus protocol? Because here you see the challenge is that the participants do not know each other. Now, if the participants do not know each other, then how you are going to apply a message passing based algorithm? So the traditional distributed consensus protocols like RAFT, Paxos, Byzantine fault tolerant or BFT kind of protocols, all of them were designed keeping in mind that the environment is a closed environment and the participants know each other. Now, when the participants do not know each other, in that case, you really cannot apply those kind of traditional distributed consensus algorithm. And here comes the specific challenge for blockchain, that how can we achieve consensus even when the network is arbitrarily large and the participants do not know each other. Now, this is a kind of an open scenario, the permissionless protocol or the permissionless blockchain protocol that we are talking about. So you do not record your identity while participating in the consensus systems. Now, here comes the beauty of the Bitcoin designer, that it has invented a nice way to design a consensus protocol, or rather a crypto consensus protocol for permissionless blockchain, which is based on the challenge response based system. So the broad idea is that the network is going to pose a challenge, and each node in the network would attempt to solve the challenge. Okay, so that is the basic philosophy. So we'll see from a while what this challenge is and how this challenge is going to work. So the challenge response based protocol, the broad idea is that the nodes in the network tries to solve some challenge posed by the network. And in this case, the beautiful aspect in this design is that the nodes or the participants do not need to know each other or do not need to reveal their identity. What they are simply doing, whatever challenge they are going to get from the network, they are going to solve that challenge. Okay, and the entire idea is that the node that is able to solve the challenge first would get to dictate what the next set of data or state elements to be added should be. So it is something like that. See, I basically want to elect a leader in an open environment. Well, in an open environment, see, whenever you want to design a kind of consensus, the first principle is that you should have a leader. And the purpose of the leader is to propose something such that others can either accept the proposal or they can reject the proposal. Well, so for example, in that lunch example that I have given you earlier, so I can be a proposer or I can act a leader, and I can give a proposal that, well, let us go to restaurant A. Now all of you can either accept my proposal or you can deny my proposal. Now if majority of you are accepting my proposal, that means we reach to a consensus that all of us are together want to go to restaurant A. But if majority of you are denying my proposal, then collectively we agree that, well, all of us actually want to go to restaurant A. Okay, so this is the basic principle. So there need to be some leader or some proposal who is going to propose something, and the basic challenge comes here that in an open environment, how you are going to select a proposal. And this kind of challenge response based protocol is actually helping you to elect a leader or a proposer without revealing the identity of individual nodes. So the network is posing some kind of complex challenge. Assume that that complex challenge is a kind of mathematical problem, a cryptographic problem. Everyone tries to solve that. So the person or the participant who is first been able to solve that particular challenge or a particular mathematical problem or a cryptographic problem, that person says that, hey, I have solved a problem, so I am the leader. Well, now the entire beautiful part is that, well, you need to design the challenge in such a way so that the challenge is difficult, but verification is easier. So I can give a mathematical problem as a challenge. So I need to design the mathematical problem in such a way so that the solving the mathematical problem itself becomes difficult. Because if you make the mathematical problem easier, then everyone can solve it immediately, and everyone can say, hey, I have solved it, so I am the proposer. So I do not want that. What I want to give you a sufficiently difficult problem so that every one of us need to spend considerable amount of time to solve that problem. And once you solve the problem first, should be able to say that, hey, I have got the solution and here is the solution. Now the verification of that solution need to be easy, such that everyone else can actually verify that from the result. So once you are getting the result, everyone of others should be able to verify that the result that has been obtained, it is a kind of solution of the problem. So that particular verification need to be easier, and everyone can verify that, well, the challenge has actually been solved by this particular guy or this particular participant, and he is the actual leader. So whatever he is proposing, now we are going to give the vote. Well, so that is the broad idea of this kind of challenge response based protocol. So what we have to ensure, that I have mentioned, that I need to design a good challenge. Well, so you need to ensure that different nodes will win the challenge at different rounds. So you need to ensure sufficient diversity in the network. Say, if a single node always wins the challenge, then the problem is that you are introducing monopoly in the system. So that person will be able to detect what is going to be the state of the system at every round, and that way, whatever that person is dictating, that is going to be the output of the system. So that way you are introducing monopoly if the challenge is easier and the challenge is not sufficiently random. So you need to ensure that, well, the challenge that is given, first of all, not a single node will be able to win the challenge at every different round. Rather, different participants will win the challenge at different round, ensuring that the output is truly decentralized. So in one round, I become the leader by solving the challenge. In another round, one of you become the leader by solving the challenge. In the next round, a third person may become the leader by solving the challenge. And that way it can go on. Well, and this ensures that no node would be able to control the network. And the Bitcoin proof of work algorithm actually ensures a consensus over a permissionless setting based on the challenge response. So the entire idea that I have explained to you till now, that is basically implemented in the Bitcoin proof of work algorithm. So there is a kind of nice economics behind the blockchain consensus. Apart from this from that technical perspective, like the technical challenge, solving the challenge and solving the mathematical problem to get elected as the leader and proposing a new block. Apart from that, there is another economic factor, which is again a very interesting idea behind the Bitcoin consensus protocol. So, if you look into the challenge response based architecture, so what I have mentioned that this challenge response requires that every node spend large amount of computational power to solve a mathematical challenge in each iteration of consensus. Well, so I need to design the challenge in such a way, as I have mentioned, that the challenge need to be a complex challenge. It should not be an easy challenge, and you need to ensure that different participant wins the challenge at different round. Well, to ensure that, what you have to do, you have to ensure that the participants who is been able to find out the solution of the challenge, that participant has spent a huge amount of computation power in solving the challenge. Okay, so the question comes here that why the participants or why the nodes are going to invest that computation power. So what is the incentive for the node to participate in this challenge response based system? Well, because at every round, many participants are actually participating in these things. Everyone is trying to solve the challenge. Okay, so a challenge has been posted among these 94 participants who is there in this session, and we got the challenge from the session organizer. Say that is my network, and every one of us are trying to solve the challenge, and every one of us are actually investing a huge amount of computation resource to solve the challenge. So what is going to be the incentive for us? So that is a kind of important question. So here comes the concept of digital money that basically Bitcoin introduces. It ensures the operational efficiency, and it provides more levels of controlling the monetary policy. Now, this concept of digital money was actually introduced in 1998 by Wedai, who published a concept called B-Money, which is an anonymous distributed cash system. And successor of that B-Money is the cryptocurrency. So the basic philosophy behind cryptocurrency is the currency which is beyond the control of banks and government. So I'm not going to cover that part, like why it is beyond the control of government or banks. So I hope that you will have other talks where you can understand about the openness of this cryptocurrency system. But what we want to look into that once I am controlling the entire system within such kind of digital money, and if I ensure that the participants who are trying to solve that particular challenge, and this procedure in terms of Bitcoin, we call it as a mining procedure. So the mining ensures that no node has the power to sabotage the network and gain control. That means no one can hold the control of the cryptocurrency. So the computation effort that is given by individual miner who are actually mining the new block, that means who are going to find out the challenge which has been imposed by the network, they get certain incentive in terms of cryptocurrency. So that means whenever a miner is successfully being able to mine a new block, he or she will get some amount of cryptocurrency. So that is the incentive for the mining. And that way, everyone will get motivated that, well, let us participate in the mining procedure, although it is probabilistic. But if I somehow win this particular challenge in this round, I am going to gain some amount of cryptocurrency. So that way, in one side, it is providing an incentive to the miners, and at another side, it is always making a control flow of currency or the control flow of money in the market. Well, so in the same way, the money flows in the market. So new monies are introduced, the new coins are introduced in the market. So that way, new cryptocurrency get introduced to this mining procedure. So that is the kind of nice economics which is there behind this blockchain consensus or the Bitcoin consensus protocol. So as I have mentioned, that the traditional distributed consensus protocols are based on message passing or shared memory. So it is based on message passing when individuals are connected over the internet, and it is based on shared memory when a common memory place is available to read and write the shared variables. But message passing requires a closed environment. Everyone needs to know the identity of others, and shared memory is also not suitable for internet-based computing because there is, if it is a kind of very large network or there are large number of participants, so shared memory-based system gets very slow. On the other hand, if you think about the traditional Bitcoin blockchain, it is an open environment. Anyone can join in Bitcoin network anytime. And the question comes that how do you ensure consensus in such an open system? So that is the key challenge behind designing the consensus protocol for Bitcoin. So before going to the detail about the consensus protocol in Bitcoin, let us ask the question, like, why do we require the consensus in Bitcoin network? Now, I guess that you already know that Bitcoin is a kind of peer-to-peer network. So there is no centralized control, and everyone is actually maintaining a local replica of the entire blockchain, entire Bitcoin blockchain. And whenever new blocks are getting added in the system, the copy of the blocks is updated in the local replica of all the participants. So in typical peer-to-peer Bitcoin network, say Alice broadcast a transaction in this peer-to-peer network. Now, all the nodes in this network need to agree on the correctness of this transaction, right? So that is the first principle to ensure the correctness of the system. So the challenge that we have, as I have mentioned several times, that a node does not know all the peers in the network because this is an open network. So there can be some nodes which can also initiate malicious transaction in the network, and you need to ensure that these malicious transactions are not committed in the network. Okay. So you need to ensure that only the correct transactions or only the genuine transactions get committed in a block. Now, in Bitcoin network, every node has block of transactions that has already reached into the consensus. That is our starting point. So I already have a blockchain. Well, so that is the block of committed transactions. So how we initiate it, I will commit later on, but for the time being, assume that I already have a blockchain. That means I already have a few blocks of committed transactions, and new transactions are being generated in the network. Okay. So the nodes also has a list of outstanding transactions that need to be validated in the block of committed transactions. Any question or any comment? I see there is a question here. I am going to take that question after reaching a checkpoint. If there is any other question, you can actually ask, or I can go back to the So let me go back to the top. The nodes also has a list of outstanding transactions that need to be validated against a block of committed transactions. Okay, that is basically my objective. So here is this entire architecture. You have these blocks, already have the blocks. So I know that you already know this data structure. Every block is connected with its previous block to this previous hash. This previous hash actually contains a nonce factor, that is this nonce is connected with the previous block hash, and I have a setup block. So in this setup block, I have the transaction root, where the transactions are organized in the form of a market. Okay. Now, I get a new set of transactions, say TX12, TX13, 14, 15, 16, and 17. And this new set of transactions need to be committed and need to be added to this existing blockchain. Okay. So that is my objective. So the question comes that how I am going to add this new set of transactions to this existing blockchain. So there are two ways consensus can be reached. Okay. So just a request. So I am getting some noise. So if someone is not asking any question,
excuse me, Murari Singh, please mute yourself, Murari Singh. There are a lot of noise is coming. Murari Singh.
Yes, sir. Yes, sir. Yes, sir. Okay. Sorry, sir. Sorry.
Okay. Okay, Sandeep sir,
Yeah.
carry on.
Thank you. Thank you. Yeah. Uh, so in the previous example, as I was mentioning, that this set of new transactions need to be committed and need to be added in this existing blockchain. Okay, so that is my problem. Now I can reach to the consensus in two different ways. Either I can commit individual transactions or I can commit a block of transactions. So I can individually commit TX12, one TX12 is committed, then I can commit TX13, one TX13 is committed, then I can commit TX14. That way I can do the commitment. Otherwise, I can take all these pending transactions from TX12 to TX17 and commit them in the form of a block. Now, if you compare these two things, that this part transaction consensus is inefficient because for every transaction, if you ask the miner that you solve a complex challenging problem, the miner is not going to do that. Okay, so that is going to be a lot of overhead, and for every transaction, it will take a lot of time to commit the transaction in the network. Well, so that is why what we do, that we use block-based consensus in Bitcoin. Well, so we have a block of transactions which contains a set of transactions, and this entire set of transactions are committed in the form of a block. And from here, actually, the name blockchain came. And that is the basic principle, that why we are organizing these entire transactions in the form of block, because committing the transactions in an existing blockchain is easier by running the consensus on top of a block rather than on top of individual transactions. Okay, so these block-based consensus are much more efficient, and you can understand that, or you can think of that. Like for every transactions, if you need to run the mining procedure, that is going to be a significant overhead. Right? That's why we are going for a block-based consensus. Now, now think about a Bitcoin peer-to-peer network. Okay, so in a Bitcoin peer-to-peer network, I already have a blockchain. So here in the right-hand side, you see that there are 3 blocks which are connected. So that is the existing blockchain, and people are generating transactions. And when people are generating transactions, one of the first principle is that your network is asynchronous. Network is asynchronous means everyone may have not seen all the transactions at that instance of time. It might happen. So here I have given an example of 3 miners. It might happen that a miner 1 has seen transaction 15, 16, 18, 19 and constructed a block out of it. Miner 2, it has seen transaction 15, 16, 17 only, and it has constructed a block out of it. And miner 3, it has seen transactions 15, 16, 17, 18, and it has constructed a block out of it. Okay. So because of the asynchronous nature of the network and the delay which is there in the network in transmitting the message, this can always happen in case of a large network. It is not necessary that everyone will see all the transactions which are going through in the network. Okay, so every miner or every participant who is there in the mining procedure, they can have individual blocks in their hand. Well, now the question comes, the objective of this Bitcoin consensus is that which block do we add next? So we already have 3 blocks. Now I need to select one of these 3 blocks and add this block to this existing blockchain. So the challenge that I have, as I have mentioned several times earlier, that these miners, they do not know each other. Okay, so if the miners know each other, they can simply apply our traditional distributed consensus protocol like Paxos, Raft, PFT, those kind of protocols, and they can agree among themselves that, well, let us commit this green block. Okay, so but that kind of agreement is not possible here because the miners do not know each other. Well, as I have mentioned, that one possible solution could have been that broadcast the information and then apply a choice function. That is the traditional distributed consensus algorithm, but it is not possible. Okay, and this kind of solution is also not feasible because remember that it is a complete distributed system. Okay, and every individual miner is running the system on their own machine, and you do not have a global clock. Well, So the question is that how much time you will wait to hear the transactions, because the clocks of individual machines may not be synchronized, and that is true. You cannot have perfect synchronization across all the clocks in a distributed system. Even the clocks in my laptop is not similar to the clocks of your laptop or your desktop or your mobile. Okay, all of the clocks are different and they are running independently. Okay, so this actually comes from something called the impossibility result. I am not sure whether you have already heard of that or not. So the impossibility result says that in a perfect asynchronous system, it is impossible to reach to a consensus. Okay, so if your system is showing such kind of asynchronous behavior where there is a delay in transmitting the information and the clocks are not synchronized, in that particular case, you cannot get a perfect consensus solution. Now we have a few observations here based on which we design our consensus algorithm. So the first observation is any valid block can be accepted. Okay, a valid block means a block with all valid transactions. If the transactions within the blocks are valid, and if you know Bitcoin, you might know that this validation is done with the help of something called Bitcoin script. So it uses a cryptographic mechanism based on digital signature and cryptographic hash to validate individual transaction through Bitcoin script. I do not have the scope to cover that particular thing here, but assume that there is some function. If you do not know that validation procedure, assume that there is some function through which you can validate individual transactions. Now, if you are validating individual transaction and if all the transactions in a block are valid, that means the block is valid. Now, in a Bitcoin, the first observation is that we can accept any valid block. There is no requirement that the red block need to be accepted or the green block need to be accepted or the blue block need to be accepted. As long as one of the block is valid, you can accept it. Okay, and even if that particular block has been proposed by one miner. Okay, so there is no necessary that the same block need to be proposed by multiple miners. Your only objective is to add the valid block with the existing block. And the second observation that we have is the protocol can work in rounds. That means you broadcast the accepted block to the peers. So once a block is accepted, you broadcast it, and all the peers in the network, they can validate the block by applying the validation function. Now, once they are validating the block and they are able to find out that, well, the nonce that you have generated and the transactions in the block are valid, they can add that block to their existing blockchain. Okay, and you can then collect the next set of transactions. Now, based on this particular solution, particular observation, two observation, this Bitcoin uses the solution which is something like this, that every miner independently tries to solve a challenge. Okay, so so this miner 1, it will try to solve a challenge. Miner 2, it will try to solve a challenge, and miner 3, it will again try to solve the challenge, and they will do it independently. The block is accepted for the miner who can prove first that the challenge has been solved. So once it is getting the solution of the challenge, the miner also has to prove that, well, the challenge that is given there, that particular challenge has been solved, and that proof need to be attached to it, the block. So the question mark that I have put to it, all this red, green, and the blue block, so that question mark will be replaced by the proof of solving the challenge. And from there, the term proof of work comes. Okay, so we are attaching the proof along with the every block. So once you are getting the solution, the miner broadcasts, hey, I have the solution, and to all the miners. Now everyone can see, everyone can validate that, well, the transactions are correct. That means the block is correct, as well as the solution is correct. So once that becomes correct, then this and this particular communication can work asynchronously. Well, and once this validation is being done, so the block can be added to the existing blockchain. Okay, and this is actually the mining procedure. Okay, Bitcoin uses a specific challenge through this cryptographic, the one-way utilizing the one-way property of the cryptographic hash function. But you can design any kind of network challenge. But the basic primitive is that once you are getting a solution, you have a proof of that solution, and you can add that as your block. Now, all other nodes can see that transaction 18, 19, they have been committed, but transaction 17 has not been committed. So you add transaction 17 in the next round. So again, in the next round, you construct the 3 blocks with a new set of transactions, new set of uncommitted transactions, and run it again. Okay, so that way this entire procedure can work in rounds, and new blocks get added to the blockchain. Now, this concept of proof of work, it is basically an economic measure to deter service abuses by requiring some work from the service requester. That means whenever you are solving the challenge, as I have mentioned, that if you are going to give some easy challenge, everyone is going to solve that quickly. And again, you are in a dilemma that who has solved it first. Okay, so the challenge needs to be sufficiently complex so that it can take some time. And at the same time, only the miners who are interested to solve the problem, they can participate in the mining procedure. Not everyone participate in the mining procedure. So this idea of proof of work actually came from Dork and Naur in 1992 to combat the junk email. So that the idea was that you have to do some work to send valid email, and the attacker would be discouraged to send junk email. So that way you need to attach some proof with every valid email, and that particular concept was called hashcash. Okay. Now for proof of work, the feature that we have is asymmetry. So as I have mentioned, that the challenge that is being given, the challenge need to be sufficiently hard but feasible. So people should be able to solve the challenge, but the validation must be easier. So the work must be easy check for the service provider. So once the solution has been found out by one of the miner, others should be able to easily validate it. Okay. Now, the interesting fact is that we can use the cryptographic hash function as a challenge for this proof of work mining mechanism. Now, if you know the idea of that cryptographic hash, you know that there is some property of cryptographic hash which is called the puzzle friendliness, which says that given x and y, it is difficult to find out k such that y equal to hash of x append k. So in this particular hash function, you know x and y, and you need to find out k. And finding out such kind of k is very difficult, but not infeasible. So you can do a kind of iterative search or a kind of exhaustive search to find out this k. Well, but there is no standard algorithm through which you can find out the value of k. So what you have to do, you have to try with different values of k, and you need to check that for which values of k, hash of x append k becomes equals to y. But once you have obtained a k, that means once you know what is the value of x and what is the value of k, it is very easy to generate y. Okay. So although it is difficult to find out the values of k, but it is easy to find out the value of y if you know x and k. Now you think of from the miners perspective. The miners need to find out k. Okay. So that is challenging. So the miners have to try with different values of k, and they have to find out a k such that y becomes equal to hash of x plus k. But once a miner has obtained this k and put it within this question mark in the solution space, then other miners can easily validate it, because now the k is known. So you put the value of k, compute the hash value for x mod k, and check whether it becomes equals to y or not. If it becomes equals to y, then you are done. Okay, you can validate that well. Whatever the value of k has been found out by one miner, it is a valid value of k. Well, so that way, it is difficult to find out the solution for the challenge, but it is easy to verify the challenge. So in case of Bitcoin proof of work, what we do actually, so we have the block hash. So every block has some hash value. We have the previous block hash. So every block, it contains the hash of its previous block. The Markley root is, if you know the organization of these blockchain transactions, the transactions are organized in the form of a tree kind of structure that is called a Markley tree, and the root of the Markley tree is called a Markley root. And I have a value called nonce. Okay, so this nonce actually works like a proof. Well, so the hash function that is given as a challenge for Bitcoin miners is that BH, that means block hash, should be equal to certain hash function. So in case of Bitcoin, it is SHA-256 hash function, or basically SHA-256 that is applied twice. We call it double SHA-256 on the previous block hash, the Markley root, and the nonce. And the task of the miner is to find out this nonce. Now you see, if you can find out the nonce, then using the previous block hash, the Markley root, and the nonce, you can easily verify that whether it matches with the block hash. Well, and the thing is that if you want to tamper this particular blockchain, what you have to do, you need to make the change. You need to make a change in the transaction. Now, if you want to make a change in the transactions, your Markley root will get changed. If your Markley root is going to get changed, you need to make a change of the previous block hash. That means the nonce to make it work. And changing this nonce is a difficult stuff. So that way, such kind of architecture actually prevent the attackers to make an attack on the system, on the particular system. So as I have mentioned, that most implementation of Bitcoin proof of work use double SHA-256 hash function. So the miners, they collect the transactions for 10 minutes, which is the default setup. The probability of getting a proof of work is low. It is difficult to say which miner will be able to generate the block. So that way, different miners will be able to find out the nonce at different rounds, and no miner will be able to control the Bitcoin network single-handedly. Okay. So this is all about the consensus in the permission blockchain system. I would take a break here, and I would just try to see if you have any question, and I would be happy to answer the question. Before taking up the questions further, I see there are a few questions which have already been posted here. So let me take up those questions first. The first question was from Chaiti Sarkar. Is there any measure to check whether the person who solved the problem earlier is right or not? Yes. So the example that I have given here. Okay. So your task is to find out the nonce. Well, now once you are finding out the nonce, this nonce is appended in every block. So that way, once you are getting this nonce, having the Markley root and the previous block hash, you can compute the block hash and check whether that block hash is matches with the current block hash or not. Okay, that way you can validate it. So the validation is easier. Then from Ramesh Babu, you mentioned as share memory is not apt for Bitcoin, then how it would be good when there are many users. Does cloud comes to act at this point? Actually, shared memory is not good for large network because even in the form of cloud, everyone need to communicate with the cloud, need to put there is also a security concern. If the cloud fails, then what is going to happen? Well, from that particular aspect, shared memory architecture works good for a small network, but for a large network and for an open network, that is not a kind of viable solution. It actually brings, even if you are going to use cloud, it brings a single point of failure. So that's why typical blockchain designers, they tries to avoid such kind of architecture.
Sandeep sir,
yeah.
I have one question. That is there any possibility that the two miners can solve the puzzle at the same time?
It is possible. It is possible. It is always possible to do that, and that is why in Bitcoin there is a concept called fork. So it might happen that two miners solve the puzzle at the same time, and in that case, both the blocks becomes valid and they get appended on the previous block. Now what happens over time? So in the next round, when the next block is getting added, then the next miner is going to choose one of those previous blocks and append it with that. So that way, over time, one of the chain is going to be the longest chain, and that longest chain is actually considered as the valid chain in Bitcoin, and the other sub chains which gets created because of such kind of problem, they called as the fork, okay, or the orphan block. So these orphan blocks are, although they are the valid blocks, but they are not part of the main chain, and that's why the transactions which are already been committed in an orphan block, those transactions need to be mined again and need to be added to the longest chain.
Okay,
so that's why there is a term called consensus finality. This kind of open consensus protocol actually doesn't support finality. That means even if you are adding up a block, you do not know at that point of time whether that block is final or not. After some time, you will be able to see that, well, this block becomes a part of the longest chain, so that block is final. But there is no way to immediately say whether that block is final block or not.
Okay, sir. Thank you, sir. So there are some other questions also.
Yeah, there are some other questions. One question is from Jignesh Vania. If any transaction is waiting to get validated and meanwhile it is updated and resubmitted, then there will be two transactions. So, okay, so this is basically called double spending. And in case of Bitcoin, what happens that the transactions which have been processed first, it is committed, and the second transactions which is coming, then the miner will see whether the second transaction is getting a conflict with the first transactions or not. If there is a conflict, it is going to delete that transaction or drop that transaction from the consensus space. Now that is why, and you remember that this entire blockchain structure is immutable. Once you have issued something, you cannot revoke it or you cannot update it. Well, to update something, what you have to do, you need to revert that transaction. That means you say, if you have transferred, say I have transferred $100 to say Dr. Patnaik, okay. Now I have decided that, well, I do not want to send $100, rather I want to send $200. Now what is my option? I have two options. Either I initiate another transactions of sending $100 more to him, or the second option is I make a reverse transaction. That means I initiate a transactions of -100, then initiate a fresh transaction of 200. Well, so this is easy for if you are adding up, but say if I want to reduce, say I initially initiate the transactions of $100, and I want to reduce it to $50. So what I have to do, I have to first initiate a reverse transaction of -$100, then a fresh transaction of $50. Okay, so that is the standard procedure. So you cannot update any existing transactions. You need to initiate a transaction, reverting or invalidating the previous transactions, and then adding up your new transaction. Okay. Otherwise, the miners may find these transactions conflicting and they may drop it from committing. Then the next question is from Vishwajit Datta. Is there any timestamp after which we perform consensus? Yeah, that I have mentioned that typically at every 10 minutes, these miners collect the transactions and try to perform. But this 10 minutes is a rough 10 minutes because it is an asynchronous system. So you cannot perfectly say when that boundary of 10 minutes gets ended. Okay. So you approximately when the 10 minutes get ended, you add up the next block. The next question is from Suripta Mandol, who is going to design the challenge. This is default for different kind of blockchain networks. Say for example, for Bitcoin, the challenge is fixed. It is like the hash function is SHA-256, and there is a parameter called difficulty. Depending on that, you need to ensure that, well, the target hash that you are going to generate, the first few bits, say the first n number of bits for that target hash is going to be 0. Okay, so that way the challenge is designed. And for Bitcoin, there is one challenge. For Ethereum, there is another challenge. For individual blockchain developer, they design the challenge and they make the challenge a bit dynamic. Like in case of Bitcoin, as I have mentioned, that the first n bits of the target has need to be 0. This value of n gets changed over time depending on some complex formula that I am not going to discuss here because of the timing constraint that I have. But you can look into this difficulty parameter in Bitcoin, and that difficulty parameter in Bitcoin will give you the details. Okay. The next question is from Ravindra Kerkar. What will happen if one of the miner is disconnected from network during the consensus? Nothing will happen. Other miners are there. And as I have said, that this is a complete asynchronous system. Everyone is trying to find out the solution independently. Okay, so if someone gets disconnected, fine. That particular miner will not be able to propose the solution. There are others miner who will be going to propose the solution. Okay, so this particular thing works independently and asynchronously. Another question from Suripta, so that I have answered. Ravindra Kerkar, that can anyone hack the answer during transmission for submission? Actually, hacking that transaction is kind of not possible because we use the concept of digital signature along with the nonce. So whenever a new block is proposed, the block is actually encrypted with the digital signature of the miner who is actually proposing the block. That way, there is always a stamp that which miner has originally proposed the block, and you cannot tamper it. So I'm not going to the concept of digital signature, but you can, if you do not know what a digital signature is, you can think of it a kind of digital replacement of the physical signature. So whenever a miner is generating a nonce, the miner is also digitally signing so that others cannot steal it. Question from Ranjana Goswami. Who validates the validity of the block? Everyone in the network, because it is a complete decentralized system. Okay. So whenever I am keeping my local copy of the blockchain, and whenever I am keeping my local copy of the blockchain, and one new block has been proposed, before accepting that block, I would validate the block and then only add the block to my existing local replica of the blockchain. So that way, every participant in the Bitcoin network is going to validate the block. Is there a single solution only to a challenge? No, there can be multiple solutions. And if you can find out one of the solutions, that is valid. And that way, the question that has been asked by Dr. Patnaik, that there is always a possibility that multiple miners can find out the solution simultaneously. And these two solutions can be a different solution, may not be the same solution. One question from Natasha said that what will happen if all Bitcoins are mined? Actually, people are thinking about that, and there are multiple alternate proposals. One is proof of stake, another is to continue proof of work. But rather than having some kind of incentive which is being generated by the network itself, you issue a transaction fee, and that transaction fee can be used as a kind of reward to the miner. Okay, so that was the kind of proposal in case of Bitcoin. Who will remove or handle the orphan block in the network? Again, it is a decentralized system. So the miners can find out, or every node can find out which are the orphan block. So remember, that is a kind of open system. Everyone can see what is going on in the network. I can see that which are the orphan block, and then I can see whether the transactions which are there in the orphan block, they have been committed to a valid block or not. If they have not been committed and I am a miner, I can take up those transactions and start mining another block. Okay, and nothing is deleted from the blockchain. Even the orphan block remains there in the blockchain. But while processing, we take the longest chain. So ultimately, the blockchain, Bitcoin blockchain structure that you get, it's not really a chain. Rather, it is a kind of tree. And in that tree, you take the longest chain. Question from Madhukar Dubey. Blockchain related to cryptocurrencies is getting used because miners are getting some money benefits in terms of cryptocurrency. And if I talk about some other blockchain implementation in supply chain or any other application, then what are the benefits of blockchain? So that depends on your implementation. So for example, in case of permission blockchain, which is typically used in supply chain management, I will see if I get time to talk about that. So in that kind of particular blockchain architecture, there is no miner. So they are actually we used a traditional distributed consensus protocol such as PBFD, Byzantine Fault Tolerant Consensus. The concept of miner is only there in case of open network or open blockchain network or permissionless blockchain network. Say for example, in case of Bitcoin, they get cryptocurrency. In case of Ethereum network, they get something called gas, which is the unit of a coin for Ethereum network. That way, for different cryptocurrency, typically the most relevant application for permissionless blockchain is the cryptocurrency, and they get it in some form, some unit form. Dr. Arun Kumar, how to design a challenge so that different nodes will have different challenge level? So what you need to ensure here that you have put sufficient randomness in the challenge. Okay, if the challenge is not sufficiently random, then a single user or a single participant can solve it all the times. Now, how you are going to introduce randomness in the system? Typically, the cryptographic functions like SHA-256 function, it introduces that randomness. So if you want to know more detail about that, I would suggest you to look into these cryptographic hash functions and how they are being designed and why you do not have a kind of unique solution for that kind of hash function. So if you look into the details of cryptographic hash, you will get to know about that. Okay, is there any other question, or otherwise I can quickly go to that permission blockchain consensus in the next 15 minutes.
Okay, sir, you can go ahead. There are no queries further.
Okay, thanks. Well, so let me talk about the permission model. This concept of permission model came from the fact that blockchain can be applied just beyond cryptocurrency. So, for example, say in case of supply chain management or within the closed enterprise, there can be a few number of participants who want to share some data among themselves, but they really do not trust each other. Okay, so this such enterprise use cases have only involved a few 10 to few hundred known participants. So that is not really a closed network. Rather, that is a kind of open network. Now, this permission blockchain, the idea of the permission blockchain, that was based by leveraging the 30 plus years of technical literature that talks about different kind of consensus protocol for distributed systems. So the name that I was mentioning earlier, like Raft, Paxos, or Byzantine fault tolerant algorithms. So in case of a permission model, that is a blockchain architecture where the users are authenticated a priori. So in contrast to the permissionless model where the participants are open participants, they do not authenticate themselves, anyone can participate. But in case of a permission model, the participants need to be authorized or authenticated a priori, and the users know each other. So when the users know each other, I can use the traditional distributed consensus algorithm. However, users may not trust each other. So the security and consensus are still required. Well, so that means you run the blockchain among the known and identified participants. So one of the use cases that I was mentioning is the supply chain, so the provenance tracking of assets. So you have the supplier who are supplying something, then it is going to the distributor, to the vendor, to the market, and there is auditor who want to check that how things are moving across different participants. And here you see that the supplier doesn't trust distributor doesn't trust the vendors. So that way, if you want to keep a kind of decentralized database of how the things are moving in the market, you want to take a log of it, blockchain can be a good solution. And in this particular application, you see that we do not have a kind of open environment. We have a fixed set of suppliers, we have a fixed set of distributors, a fixed set of vendors. So what we can possibly do that we can create a closed network and run the blockchain on that closed network. Okay, and here comes the concept of smart contract. So the idea of the smart contract is that within this closed network, you can run intelligent programs that will automate the stuff. So for example, whenever the supplier is distributing or supplier is supplying something to the distributor, I can write a script which will automatically deduct the money from the account of distributor and send it back to the supplier by verifying that whatever supplier had promised, the things have been supplied to the distributor. Now, this automated script can be written on top of a blockchain, and the blockchain can actually execute that, because you see the basic notion of blockchain is that all the participants has same view of the system. Now, if the supplier and the distributor has the same view of the system, and if I'm running an automated script on top of that, obviously I should not have any kind of problem. I can easily check whether the potatoes or the lemons have been delivered to the distributor, and if that many number of say buckets have been delivered that have been promised by the supplier, the money can be automatically transferred to the supplier account, and even an auditor can check that particular auditing. So this is basically realized with the help of smart contract, which are the kind of programs that are executed based on the states which are being saved on the blockchain. Now, the question comes that if you are going to design a smart contract, whether you need to execute the smart contract on all the nodes. Okay, actually the answer is that not necessarily, because say you think of such kind of a peer-to-peer network and you execute a contract in one of the node. Now, what you can do, you can broadcast the state of this contract. Say, for example, the contract says that, well, the supplier needs to supply 1,000 buckets of potatoes to the distributor. Now, this contract gets executed and it checks whether 1,000 buckets of potatoes have been supplied to the distributor or not. If the buckets have been distributed, so the system moves to the next state. And this state is broadcast to all other nodes. Now, once every node gets the state of the system, they can actually execute a consensus and find out that, well, whether the state is correct. Now, here actually what can happen, that some of the nodes can be faulty. They can behave maliciously. They can say that, well, 1,000 buckets have not been transferred, rather 100 buckets have been transferred. So that's why what we can do, we use a concept called state machine replication. What is that state machine replication? The idea of the state machine replication is that you execute the contract on a subset of nodes and ensure that the same state is propagated to all other nodes. Okay. So rather than execute it on a single node, you execute it on multiple nodes, and the output state, it is propagated to all other nodes, and the consensus is reached on them. Now, let me briefly talk about the state machine replication idea, which is applied in permission blockchain. Now, any kind of computer program, so whatever algorithm you are rewriting, you can represent it in the form of a state machine, right? So you have certain input. Based on the input, the system moves from one state to another state and outputs something. So I hope that you remember the concept of that melee machine, mood machine, that kind of things. Okay, so you have a kind of state machines. Now, any kind of smart contract can be represented as a state machine. So here is an example. Say you initiate some. So this is an example from a crowdfunding environment. Crowdfunding means you have some project and you are requesting money for that project. And if you reach some milestone of that project, then the money will be transferred to your account. So you can represent the crowdfunding with such kind of state machine. Say you initiate the job, and there are two donors who are donating the money, Bob and Alice. Say Bob transferred the money that he has committed. So you reach to the state Bob donated. You initiate, then Alice transferred the committed money. Then you reach to the state Alice donated. So after Bob donated, if Alice has also transferred, you reach to the state money available. After Alice donated, if Bob donates, then both Bob and Alice has donated. So you reach to the state money available. After that, you have the money, you start the job. So once job 1 done, you reach the state job 1 complete. After that, job 2 done, you reach to the state that job 1 and 2 complete. In the other order, if you first complete job 2, then job 2 done, then job 1 done, you reach job 1 and 2 complete. Now once the entire job is complete, the remaining money is transferred from Bob and Alice. So that way you can replicate any kind of contract in the form of a state machine. Now, in case of distributed state machine replica, you place the copies of the state machine on multiple independent servers. So here, say in my previous example, the distributor, the vendor, the supplier, everyone is running their own copy of the state machine. Now, when some input is being received, you execute locally on your state machine and find out what is the current state and broadcast that information to all other servers. Well, after that, you take the next input and again run your state machine and broadcast it. And that way, everyone is actually on the same page and everyone can see that what is happening in the system. And based on that, you keep on executing the system until the contract is executed completely. So that is the idea of the state machine replication. Now, in case of permission blockchain, we can use this concept of state machine replication. So there is a natural reason to use state machine replication based consensus over permission blockchains. First of all, the network is closed. Because the network is closed, the nodes know each other. So state replication is possible among the known nodes. So once you are reaching to some state, you broadcast that information to your known nodes and everyone updates their node. You avoid the overhead of mining because mining is always having an overhead, right? Because you are using complex computation formula or complex computation to find out the solution, and that you can avoid here. However, consensus is still required because some machines can be faulty or the machines can behave maliciously. Now, here we apply the concept of distributed consensus, and to apply distributed consensus, if there is one decision maker, actually we do not need any consensus. If there are multiple decision makers, we need consensus. And here actually people use the concept of Byzantine fault tolerant agreement. The Byzantine, I am very quickly going through this because of the timing constraint that we have. So in case of Byzantine fault tolerant, typically if there are 2 nodes, you cannot reach to a consensus. But if there are 3 nodes, then it is possible to reach to a consensus in the presence of crash fault, network fault, or Byzantine fault. So Byzantine fault means there can be some hardware software fault or the particular participants can behave maliciously. Okay. So there are different kind of algorithms to support these faults in case of distributed consensus. So if you only have crash or network fault, you can use algorithms like Paxos or RAF. If you have Byzantine faults along with the crash and network faults, you can use one of the protocols from the group of protocols of Byzantine fault tolerance. So let me quickly tell you about what is meant by Byzantine fault tolerance. So this concept of Byzantine fault tolerance comes from the Byzantine general problem. So it says that, well, you have a general and 2 army. Now, the general sends command to these 2 armies. So these 2 armies are at the, say, 2 gate of this fort. Okay, so the general actually sends the command to these 2 armies. Now, if the general is sending a command like attack to both the army, then it is fine. You are in a good shape. If they are sending a command like retreat, again you are in a good shape. Everyone is on the same page. But if the general is faulty, okay, if the general says attack to one node and retreat to another node, that kind of malicious behavior, we call it as a Byzantine fault tolerant problem. Now, in case of blockchain, what might happen? A particular Byzantine node may say to one node, one of its neighbor, that, hey, I have reached into the state S1. And another node, it can say that, hey, I have reached to state S2. So it is communicating different information to different nodes. And there comes the problem. Now, there is standard algorithm. I am not going to this algorithmic details to show that, well, using this Byzantine fault tolerant method, you can actually reach to a consensus. You can find out who is actually faulty, whether the lieutenant is faulty or whether the commander is faulty. So we typically apply this kind of Byzantine fault tolerant algorithm in case of permission model, and this practical one variant of Byzantine fault tolerant algorithm which is implementable on a real system, it is called PBFT, practical Byzantine fault tolerant algorithm, that has well adapted in consensus for permission blockchain. So different kind of permission blockchain platform like Hyperledger or Tendermint, they use this PBFT. So if you are more interested in knowing this particular stuff, I would suggest you to read it from any of the distributed system books or distributed system course, which talks about these different types of consensus algorithms like Paxos, Raft, or PBFT. There are several scalability issues for such kind of Byzantine fault tolerant algorithm, and in recent years, people are doing extensive research on supporting scalability of on such kind of distributed consensus protocols. Even in our lab, we are doing that. With that, I would like to stop and would like to take any further questions. So this is a picture from our lab during our annual retreat. So let me see if you have any further question, or I can take up the questions from you as well. So in the chat box, I do not see any further questions. So you can let me know. So the last part I have covered very quickly because of the timing constraint, but I think that I have given you some pointer. If you are interested further, you can actually look into those materials. This idea of permissionless blockchain is something very new, and there is no material over the internet which actually talks about all these internals. But regarding the permission model, there are many articles available because they are borrowing the concept from standard distributed system literature, and there are sufficiently many literature which talks about this Raft, Paxos, or the PBFT algorithm. So I suggest you to read those particular articles. If you Google it with this terminology, you can get it to know more details about that. And I think you can get my email ID. If you have any doubt or anything, you can always send it to my email, and I would be happy to answer. So that's all from my side. I see there are two questions. If dispute arises between supplier and receiver, who solves the legal problem? So typically, see, if your entire data is there in the blockchain, and based on the immutability property of the blockchain, you can actually do a cross validation that what has actually happened in your network. Okay, so that is the basic philosophy. For the auditor actually looks into that information. The auditor actually checks whether there is some kind of non-agreement depending on the data which is there in the blockchain, and based on that they can take the decision, and this blockchain actually helps to solve such kind of disputes. Okay. Another question I can see that who handles software issues preventing the nodes or miners to progress. Okay, so one thing is there. So as I have mentioned that if one or two miners is faulty and they have the software issue, that is not going to affect my network. In case of permissionless setting. In case of permission setting, it is like that there is a constraint there that at most 2/3 of the network should be correct. If there are more than 2/3 of the participants in the network are faulty, you cannot recover from those faults and your entire system will collapse. Okay, so that is a kind of assumption, or that is a kind of strong requirement for ensuring distributed consensus in a closed environment. So at least 2/3 of the participants need to be correct. At most 1/3 can be faulty. Another few other questions are coming. I can see is somebody provides platform for creating blockchain, or we need to create a network by your own. There are many open source tools. There are Hyperledger Fabric, there are Ethereum. You can use that and you can build up your application on top of that. Okay. So Hyperledger has many flavor. Hyperledger Fabric that is maintained by IBM. There are Hyperledger Indie, which are very application specific. So you can just check with these toolboxes. These are open source platforms, and you can build up your blockchain applications on top of that.
This we will discuss in lab also, no problem.
Right. Okay. Uh, Organizations in India using permission consensus. I know that there are some banking sectors who have started using it in say your testing level. Even IBM is working with few supply chain management vendors and deployed the solutions there. So in India, bit and pieces, the government and the private agencies, they have started using the solutions. But till now, there is no large-scale deployments in India. All are in the experimental phase. Consensus and incentive is applicable for private blockchain. Consensus is applicable, as I have mentioned. You still need the consensus, but incentive is not there because mining is not there. Well, so if you look into the distributed consensus protocol, you do not have that kind of complex mathematical problem that everyone needs to solve or the miner needs to solve to generate the solution. So that's why you do not need to give any incentive to the miners. Indeed, there are no concept of miners in case of private blockchain. Okay, everyone participates in the consensus procedure. It is through message passing interface. Okay, I do not see any further questions. So thank you all for attending.
One question raised by Madhukar Dubey. How to start research in blockchain from scratch? Any guidance? Madhukar Dubey.
Okay, so you look into the top conferences which are publishing papers in blockchain. So there are different fronts through which you can start doing research in blockchain. But my suggestion is that do not blindly apply blockchain to any of the problem. I have seen that many people or many research papers, indeed, they are just taking up one of the problem blindly and applying blockchain there. Okay, majority of those problems actually do not need blockchain. Even a simple distributed database or a simple database will solve that problem. So that's why look into the top conferences like if you are interested in the security perspective, you can look into the conferences like, so I'm just typing it, CCS, IEEE, security and privacy, these two conferences. If you want to, if you have interest in the system aspect of blockchain, you can look into the conferences like OSPI, SO, SP. You can look into the conference like ICDCS, these conferences. So these conferences publish excellent papers on blockchain systems. But what I would always suggest people that to know the domain correctly, do not look into the papers from the Tier 2 or Tier 3 conferences. Many of those research papers are junk papers, and people start applying blockchain in any front. Always try to look into these top conference papers. They will give you updated information about what people are doing in the front of blockchain. So from that can be a good point to start or good point to see that what are the currently hot problems, hot research problems in the blockchain domain.
Sir, I have one question. Can I ask?
Yeah, please.
Sir, like you said, sir, in India, we have not yet fully deployed any kind of project using based on this technology. Out of curiosity, I want to know, sir, what exactly are the challenges we people are facing? Why we are not in a position to develop till date? What are the challenges?
Actually, see, there are many of the times. So in India, if you want to deploy any system, the biggest problem is our mass, okay, and our diversity. sometime means that is entirely my personal view, that monopoly is bad, but sometimes monopoly is good. So if you try to take a decision based on the view of 1,000 different pupils, or in case of India that is not even thousands, that is millions different people, and all those people has completely different views, and under this kind of settings, in terms of consensus, you will never be reached to a consensus. Okay, and that is the exact problem which is happening in India. There are diverse views. People are totally confused about whether to implement it or not. Even at the policy levels, we do not have any kind of clear policy about where to implement or how to implement blockchain-based solutions. And another major problem in India that I have seen, that is with the government officials and with different people, they actually mix up the concept of blockchain and cryptocurrency. So cryptocurrency, from the economic perspective, I agree that it might not be good. There are many pitfalls of cryptocurrency. From the commercial perspective, from the economics perspective, from the technical perspective, it is an excellent solution. But from the economics perspective, it has a lot of challenge. No government will want to have a money that is not in their control, because in that case, the government will not be able to control the monetary aspects of the country. So that's why government doesn't want that, and that is the reason the governments do not want cryptocurrency. But people actually confuse cryptocurrency with blockchain. So people take a general decision that, well, because cryptocurrency is bad, blockchain is also bad. Well, so that kind of perception is still there in our mindset. And to have a kind of exact deployment or a kind of large-scale deployment of the system, I believe that first of all, people need to be educated, and they need to be ready to accept the technology. So that is the major pitfall that we have.
But can we easily implement private blockchain if public blockchain is having so much big challenges we are facing? Like
this private blockchain we can implement, and that's why I'm saying that at the private level, people have started using it. I know a few companies, even I am working with a company, I cannot disclose the name and all these things because of the agreement, that NDA that I have with them. But I know that a group of companies, they are using blockchain for supply chain management in the cotton industry domain. Okay, so in a cotton industry, there are a lot of challenges, like the cottons that are being produced. After you are coloring it, it is very difficult to actually find out the quality of the original cotton. So that is why there people are actually using blockchain to connect the farmers to the final producers who are going to produce the product out of the colored cotton, and connecting this entire supply chain with the help of blockchain. And that particular system is currently in deployment, and people are using it. So that was I was mentioning, like within small patches, there are systems where people are using that, but at the government level, at a large scale, we do not have that deployment. But if you look into some other countries, one country I would like to mention here, it is a very small country. I'm not sure how many of you have heard about that country. It is called Estonia. So Estonia is a European country that is near the border of Russia at the western side. Estonia, so there is a site called eEstonia, eEstonia, eEstonia. So you can actually look into this site eEstonia, and you can see that for different citizen services, they have started using blockchain. Okay, so Estonia is one of the first countries there who have deployed blockchain at different government levels. Then Singapore is another country. Singapore has the government supply chain. Currently, it is entirely managed by blockchain. Okay, so in different public service systems, they are deploying blockchain. Well, but in India, I know that government has taken some initiatives, but all those are still in the experimental stage.
So I'm thinking to create one project using this technology. I request, if possible, will you guide me, sir, on this, because I'm
We
not
can we can
getting a
discuss
proper
it. Just
handle.
drop me an email. I can set up a separate call and we can discuss.
Okay, thank you so much, sir.
One query was there relating blockchain with cloud technology.
These are actually two completely different technology. Means this is something like forcefully you do not need to connect blockchain with cloud. Okay, there might be some applications or something, or even some computation nowadays we run blockchain on top of cloud. So if you look into the implementation of hyperledger fabric or ethereum, they run on top of cloud, but forcefully we actually do not need to connect them. Okay, if some application demands, we can do it.
Okay. Last question. I have a doubt that how cryptocurrencies are created.
Just like any other monetary system. So if you think about, like, say, you have the Indian currency, how you are going to get the dollars? Either you have to procure some dollar by selling your Indian currency. That way you can buy cryptocurrency. Otherwise, say any mint, the government mints, they generates new money, depending on the economic inflation, depending on the current economic conditions of the country. Okay, so the Indian government, the RBI take decision when they want to print new notes. New notes, I'm by new notes I'm not saying about replacing the existing old and torn notes that are sending generating new notes, completely new notes, and giving it to the money. So I do not understand all those economic stuffs, but there is a economic regulation which does that. In the same way, in case of cryptocurrency, whenever you are mining, that mining procedure, the way you are getting the incentive, that incentive is actually helping you to generate new cryptocurrency in the system. Okay, so that way the new cryptocurrencies are generated. In other words, you can say if someone has cryptocurrency, you can buy the cryptocurrency from that person by giving money to them. Okay, so it is similar to other monetary systems.
Somebody asking, is Bitcoin not a parallel economy?
Exactly, it is a complete parallel economy, and the thing is that with such kind of economy where there is no control of the government, these are the kind of debatable question. Actually, I do not want to answer that because I am not an expert in economics. But what I have heard from different people, that with such kind of open market, the major problem is that you do not have any kind of control over the market. So that means if some terrorist is procuring something with the help of Bitcoin, it will be very difficult for the government to actually track it. Okay, so that's why this kind of complete open market, none of the government are actually in favor of that.
Okay, thank you so much, Sandeep sir, for your valuable suggestions and discussing your views on permission and permissionless blockchain technology. Thank you so much for being with us, for enlightening us with your valuable suggestions and clearing the doubts of our participants. And thank you so much, sir.
Thank you, Dr. Patnaik, for inviting me, as well as thanks to all the participants for spending the time. It was an excellent session. Have some nice interaction with you all. If you have any further doubts, feel free to drop me an email. I would be happy to answer. So that's all from my side. Hope to meet you again someday in person after this pandemic gets over.
Sure,
Thank
sir.
you again. Yeah.
Okay, thank you, sir.
Thank you.
Okay,
Yeah,
bye, sir.
take care.
Okay.
Bye bye.